Okay, here's that extreme value theorem that we talked about in the first video. Basically, it says that if you've got a continuous function on a closed interval, then that continuous function must have a highest point and it must have a lowest point. And in fact, we've seen an example of a function that didn't have any highest point at all. But if you remember, that thing was defined on a half open interval, so right, starting at a and stopping at infinity, that's not a closed bounded interval, right? So that the theorem wouldn't apply to that situation. So here's the theorem. Let f be a continuous function defined on a closed interval from a to b. So the key words in this theorem, continuous and closed interval. If you don't have those two things, this theorem has no meaning. It does not apply. So in this situation, if you've got a continuous function on a closed interval, then there exists x coordinates, right? So c sub lowercase m and c sub uppercase m in the closed interval from a to b. So these two things live somewhere in here, such that f of c little m is an absolute minimum and f of c capital M is an absolute maximum, right? So here's a picture of this situation. Here you've got a continuous function on the closed interval from a to b. So basically, like, you got a piece of string and you need to connect these two dots, right? An unbroken piece of string. You need to connect these two dots. There will be a lowest point, so here's where the lowest point happens at c little m, and here's where the highest point happens at c capital M, right? So there is an absolute minimum value at f of c little m and an absolute maximum value at f of c capital M. Here's another situation. Again, connect these two dots with an unbroken piece of string. We've got a continuous function. Here the absolute maximum occurs at the endpoint, right? So here a is equal to c capital M, and here the lowercase, right, the absolute minimum happens at c lowercase m, close to b but not equal to b. And it could be the situation that you've got an absolute max and an absolute min at the endpoints. So both of them happen at the endpoints, or neither happen at the endpoints, or one of them happens at the endpoint. So, right, you've got a few options, but we're guaranteed somewhere in there we're going to have an absolute maximum and an absolute minimum. It's also the case that we could have two locations where the absolute maximum is attained, right? So for example, if the function does this, terrible drawing. Right, so if the function does something like this, we can see here that, right, f of c capital M, right, here's f of c capital M. If I call this thing x0, right, so f of x0 is also equal to f of c capital M. There's two spots where we have an absolute maximum, right? There's only one absolute maximum value, but there's two spots where it could happen. So that's also a thing to be on the lookout for when we solve some of these problems. Okay, here's where this theorem could break down, right? So some non-examples. Here you've got a function f defined on a closed bounded interval from a to b, only it's not continuous. So, you know, in this case, we do have an absolute minimum, so a lowest point on the graph at x equals b, but there is no highest point on the graph, right? This f of c is not the highest point on the graph, right? So it's not, there's no maximum at x equals c, right? We can always get a little bit higher and higher, and then as soon as we reach c, bam, the thing jumps down here to a lower point. So there's no absolute maximum anywhere on this graph. And so that's why we need continuity to guarantee at both an absolute max and an absolute min. So here's a continuous function, only it's defined on an interval that's not closed, right? It's defined on closed A to open B. That's not a closed interval. So even though this thing is continuous, right, there is an absolute maximum at x equals a, but there is no absolute minimum, right? So the arrow indicates that this thing is descending forever, and so no absolute minimum in this case. So we really do need continuity, and we really do need closed interval in order to make this extreme value theorem work. Okay, now that we've gotten the non-examples out of the way, we want to look at the business of finding the extreme values of a function, of a continuous function on a closed bounded interval. How do we do that? Okay, so how do we find the absolute extreme points of a function, of a continuous function on a closed interval? So here would be the directions. And I'm going to draw a picture for this example, but in future examples, we're not going to draw a picture. We're just going to use analysis or algebra. So we want to find all the extreme points of the function x cubed minus 3x squared plus 1 on this closed interval from -1 to 4. So here's what this function looks like. Now, the possible extreme points can occur at one of the two types of places. Right, so we need to check the endpoints. Right, so here you can see that there's a lowest point at the end point of our closed interval. It also happens at this other spot. So also at critical values. Right, but just because you're a critical value doesn't mean that you're an extreme point. So the critical values and the endpoints just limit your infinitely many possibilities down to a couple, right? So this is not, right, once you find the critical values, that's not the final answer. You will actually need to check, right? You'll need to plug these two types of numbers into the function and see which one is the highest and which one is the lowest. Right, so for example, here it will get a lowest at an endpoint. We'll get a lowest at the critical value x equals 2. There's a critical value here at 0 that we will have to check, but we won't get a highest or a lowest, so we'll throw this one out. And then we'll check this right endpoint at 4, and it should return a highest among all of the possibilities. So among all of the infinitely many possibilities from -1 to 4, we can limit our testing to just the endpoints and the critical value. So that takes infinitely many numbers and reduces it down to a finite number of cases that we will need to check. So that's very helpful. Okay. Here's how you would actually solve the problem without having to draw the graph. Right, if you were on an exam and didn't have a calculator, this is what you would do. So to find all absolute extreme points of this continuous function on the closed interval, we need to find the critical points, because that's where we might have a max or we might have a min, and then we need to check the endpoints, because we saw that we could have a max and or a min at one of the endpoints. So we can take all of these points from -1 to 4 and just narrow them down to a couple of critical values and endpoints. Okay. Remember how to find critical values. That's where the derivative is 0 or undefined. So here's the derivative. It's just, right, 3x squared minus 6x. And so you can factor that as 3x times x minus 2. And so certainly the derivative is defined everywhere. This is just a polynomial, so we're not going to have any bad spots, right? There's not going to be anywhere where the derivative is undefined. So what we need to check is where the derivative is equal to 0. So set this thing equal to 0 once you find the derivative here. And so that says that x is equal to 0 or x is equal to 2. So here are two critical values that we need to check. And then we also need to check the endpoints, -1 and 4. So just plug them all in order, right? -1, 0, 2, and 4, right? So f of -1. So you take the endpoint -1 and plug it into the original, right? So plug in -1 everywhere you see an x, you get -3. Plug in 0 everywhere you see an x, you get a 1. plug in 2 into the original, you get -3, and then plug in 4 into the original, you get 17. So just by inspection, we can see that there are 2 locations where we have an absolute minimum, right? So the lowest y value that shows up is -3, right? So there's an absolute minimum, right, at x equals -1. There is also an absolute minimum at x equals -2, right? And then the highest y value that shows up is 17, and so there is an absolute maximum at x equals 4. So if you want to write down a final answer, right, there's an absolute min at x equals -1 and x equals 2. And the absolute minimum value is y equals -3, right? And then there's an absolute max at x equals 4, and the absolute maximum value is y equals 17. So this would be a good final answer, right? It tells us where the relative extreme points occur and what those extreme values are. So this would be a good final answer for this example.